Hey everyone, welcome back. Today I want to talk about what makes a model good in machine learning. Now if this seems like a weird question, then that's part of the reason why I'm making this video in the first place. When you think about the way that machine learning and data science are typically taught in universities and in courses, it really does make it seem like there's only one real way to tell whether one model is better than another, and that is using some kind of performance metric. So the exact performance metric you use will depend on if you're solving a classification problem, in which case you might use precision, recall, accuracy. If you're solving a regression problem, maybe it's mean squared error, mean absolute percent error. They can take many different forms. They tell you how good is this model doing on some kind of test or validation set for the problem at hand. And at first glance, it seems like, of course, this is the only thing you should use. But when you start a real data science job in industry, when you get some real hands-on experience with data science, you start quickly realizing that there's many other ways to tell whether a model is strong or not strong, besides just this performance metric. And in fact, there's many reasons why you might choose actually a weaker performing model if it does well in many of these other metrics. Now, to start diving into the specifics a little bit, instead of going through all of these metrics one at a time, talking about them, let's have a little more fun with it. Let's just do a couple of case studies. So what I'll do is present two different models that you're considering and tell you some information about them and ask the very simple question, which one is better? Which one do you use? So to start with, let's say you're trying to solve some kind of binary classification problem, and you're considering two models. The first is a k-nearest neighbor, and the other is a decision tree. Now the first piece of information I'll tell you about each model is that the k-nearest neighbor gives you a 90% accuracy on the validation data set. So let's pretend that accuracy is the performance metric that you've chosen to use. The decision tree gives you 5% lower accuracy, 85%. So looking at this row alone, just these pieces of information, seems like k-nearest neighbor is the better way to go here, better accuracy. Now I'm going to tell you one more piece of information, which is going to make the story more interesting. The k-nearest neighbor has a 1-minute inference time. What is inference time? Well, what is inference? Inference is the part of the machine learning pipeline where you have a trained model, and you're going to use this trained model to make some kind of prediction, in this case some kind of binary classification, about an unseen sample. So you can call this prediction. It's called inference more typically in statistics, so we'll be using that term instead. And so what it means to have a 1-minute inference time is that it takes 1 minute for this k-nearest neighbor model to take a new sample and tell me the result, the classified label for the sample. Why would it take this long? Well, k-nearest neighbor is a very interesting model in that it's not really a model at all. The model is your data. And the way you make a prediction about a new sample is you compare it against every single one of your training samples, find the k closest neighbors, and then do something like take a majority of the labels of those to get the predicted label of your new sample. So it could take a very long time since you basically have to, in the purest k-nearest neighbor form, search every single training data point. Now the decision tree, on the other hand, has a 1-second inference time, much faster, and it makes sense because a decision tree, even if you only know a little bit about it, essentially is just a flowchart using the features in your data so that you're not actually needing to store all the data at all. You're not consulting the training data itself. You're just consulting this flowchart, which behind the scenes is just a series of if statements. So running this new samples features through a series of if statements is going to be very fast compared to what k-nearest neighbor needs to do. So looking at all this information together, I ask you the question, which model do you use? Seems like a bit of a tough question now because the k-nearest neighbor gives you better accuracy, but the decision tree gives you a lot better inference time. And the reason it's a tough question, and the reason that there's not really an answer, is because we need to ask a deeper question, which is, what is this model actually for? Without knowing the answer to this question, there's really no answer to the question of which is the better model. It depends what this model is going to be used for. And to hit that point home, let me give you two different cases. So let's say we live in this world, case one, where this model that we're considering is used to predict the high school dropout, so probability that a high school student will drop out before completing and getting their degree. Now, if this is the case, in my opinion, you should go with the k-nearest neighbor model. Now, I do think this is definitely my opinion, but I also think there is a lot of merit and reasons why I'm going with the k-nearest neighbor in this case. Because when you think about case one, when you're trying to predict the probability a student's going to drop out, the units that you're operating on are high school students. And getting 5% better accuracy means a lot in the context of decisions impacting real human beings. So for example, you're probably going to take some action based on the results of this model. Maybe students who are expected to drop out, you'll give them more resources. Students who are not expected to drop out maybe get less resources. So when it becomes a question about outcomes of a human being, I think accuracy really is a really strong metric to go off of. or more accurately, the performance of your model is very important in that case. Now, yes, it's going to take a lot longer for each student, but again, you probably don't have that many students. You're not dealing with the order of millions or tens of millions of data points. It's typically maybe thousands maximum. So I do think the trade-off is worth it to go with the k-nearest neighbor in that case. Let's look at case 2 now. Let's pretend case 2, what if instead this was a model which was used to predict the probability that someone will click on a result for some search engine that you're creating. So we had some videos in the past where we were talking about building a hypothetical search engine for animal lovers where they type in some kind of keyword and you serve up some kind of results they might like. So although it is very important to give people a good search experience, it's not as dire of a consequence as this predicting high school dropout. It's not going to affect someone's future life outcome potentially. And so I do think it makes more sense in this case to go with the decision tree. Yes, it has 5% lower accuracy, so on average the person's not going to like this result as much, but the key insight here, and the reason that really decision tree is the only option that makes sense here, is because of this key 1 second inference time. In fact, with modern search engines, 1 second is still kind of long, but it's a lot better than a 1 minute inference time. Can you imagine typing something into a search engine and then the model takes 1 minute before you can get any results back? Nobody in this modern time is going to deal with that. They're just going to leave and go to some other search engine. So you want something that performs really, really fast, even if you're going to take a little bit of an accuracy hit to get there. So hopefully this starts opening the door for this more nuanced view of looking at models. It's not all about the accuracy. It's not all about the performance metric. The performance metric does matter, especially in cases like case 1 where you're making some decision about a human being's outcome in life. But there's many other things that could matter based on what your case actually is. So let's look at a regression problem to continue developing this story. So let's say you are considering 2 models again for regression this time. Let's say the first one is a simple linear regression model, and the other is a complicated neural network model. So you don't need to know about how either of these work. All you need to know is that neural networks are a fairly sophisticated model, and linear regression is a very simple model. So I again have some information about each model. Let's go through it. So the first one is that the linear regression takes 1 minute to train. So this is a different metric than the ones we've been looking at before. This is training time, which is that given some data set of a fixed size, it's going to take 1 minute to train this linear regression. Now using that same data set, it's going to take 12 hours to train this neural network. And this is not really an exaggeration. Neural networks are known to require a lot of computing power and a lot of time in order to properly train, just because of all of the weights that need to get calibrated. So it takes 12 hours to train this, takes 1 minute to train this. Now let's look at another metric that we haven't looked at yet, which is complexity/interpretability. I said in the beginning that the linear regression is a lot easier to understand. It's at its purest form, just y equals mx plus b. You can have more coefficients, of course, if it's a higher dimensional, but that's the purest form of it. A neural network, you can understand it, and you should, but if you think about people who don't really dabble in data science too much, it's going to take a lot of your time, it's going to take a lot of resources to fully explain a neural network to them. So this neural network is very hard to explain and interpret exactly what's going on under the hood and how it works, whereas the linear regression is very easy to explain and interpret. And finally, let's look at the performance metric for these. So this is a regression problem. Let's say we're going to be using MAPE, or mean absolute percent error, which is just the absolute percent error average from the truth. Let's say the linear regression gives you a 10% MAPE, and the neural network gives you a 5% MAPE. So the neural network is performing better. Again, it's a more complex model, so we might expect this, than the linear regression. But the linear regression has these other 2 things going for it. It's very quick to train, and it's very easy to explain to somebody else. Now again, let me ask you the question, which one is better? And of course, we need to ask the same follow-up question to have any chance of answering the first question, which is, what is this model for? What is it going to be used for? So let's say this model is being used to predict sales, but let's look at 2 different cases, which is going to drastically change the decision that we make. Let's say the first case is that it's going to be used to predict tomorrow's sales. For, let's say you own a small business or something. Let's say this model is going to be used to predict sales in the coming day, tomorrow. If you think about that for a second. That means every day you need to train a new model because you need to be using all the data up until now to predict sales tomorrow. And then tomorrow arrives, you use all the data up until then to predict the next day. So this model is getting trained on a daily basis. Now, it doesn't make sense that we would need 12 hours to train this model because that doesn't give us a lot of breathing room. For example, imagine that you start training the neural network and maybe 10 hours goes by and your computer crashes, some kind of error arises. Now you have to start all over. That's not a lot of time left. You're at 22 hours by the time this hopefully succeeds if it doesn't fail again. That doesn't leave a lot of breathing room for you to have a model that's going to be doing something effective at the end of the day. And for that reason alone, the linear regression is probably the good bet here because it only requires 1 minute to train. Even if it crashes, you have many, many attempts to try this again without needing to worry so much about not having any model at the end of the day. Now instead, what if this was used to predict not tomorrow's sales, but to predict the sales on, let's say, this day of the week next week. So if today's Monday, we're going to be using this model on this Monday to predict sales next Monday. So that's a whole week from now. Now the neural network starts looking like a lot better of a choice because yes, it takes 12 hours to train this, but we have a whole week, so we can accept a certain number of crashes without needing to worry that we're not going to have a model at all. So in this case, the 12-hour training time is not really getting in our way. The 5% mean absolute percent error is pretty attractive now, especially because when you think about time series models, it is extremely hard to predict things that are happening further and further in the future. And so predicting something a week from now with 5% mean absolute percent error is really, really impressive. And so we'd probably choose the neural network in this case. Now we haven't really taken the middle row about whether it's easy or hard to explain into this case study, but you can imagine cases where that could be important too. For example, I'm just kind of making this up on the fly, but let's say you work at some kind of big company and there's many different stakeholders in this project. So you might be the data scientist, but there's many other people on the team who are not as data savvy or educated in these data science techniques as you, but you still need to get their buy-in. You need to explain these models to them to have any chance of getting this into production because they need to trust what's going on. If that's the case, then you might make the call to use a linear regression, especially if your performance metric is not critical, as it was in case 2 here, where it would be nice to have a good performance metric, but we'll take a little bit of a worse metric if there's other things that are better. If that's the case, then you might choose a linear regression because you can go to them and say, oh, here's the formula. Here's literally the formula written out in one line for how this works. You can see that this coefficient is higher than this coefficient, therefore this variable has more of an impact than that variable. It's pretty easy to explain to somebody. Versus a neural network, not going to be the easiest thing to draw this on a piece of paper, explain exactly what's going on, because chances are even you're not 100% sure why this thing is doing what it's doing. Now I hope going through these 2 case studies was a little bit enlightening, just in terms of seeing that performance metrics are not the only thing that matters when you're training a machine learning model. There's many, many other things that matter. So to round out this video, let's go through 6 factors that I can think of. There probably are others, and I would love to hear them in the comments below. But let's just go through these 6 big ones that I feel are pretty important in deciding whether to use one model or another, and just briefly talk about each one. So the first is the performance metric. As much as I've been saying there's other things that are important, the performance metric is, of course, important. If you had like a terrible performance metric, it doesn't really matter how good the other things are if this thing's not going to be able to do its job. So you need to have your performance be generally high in some sense. It's just that that's not the only thing you should be looking at. Another one is training time. So we looked at this second example where training time played a big factor. As we move further and further in the future, we get better and better computing resources. The trend is becoming that models are able to be trained on a much shorter and shorter time frame. Sometimes every day, sometimes even more frequently, like every hour. But if you're going to train a model every hour, by definition, that model needs to be trainable in much less than an hour, more like minutes, because you can't take longer than an hour to train something that needs to be trained hourly, if that makes sense. So training time is another factor that you need to think about based on how frequently you need this model, as we saw in this case. Training volume. We didn't explicitly touch on that in either of these, but this is a very important one as well. Some machine learning models, I'm looking at you neural networks, takes a lot of training data to be effective. Other machine learning models, such as linear regression, more the simpler models, do not require as much training data to be effective at doing their jobs. To give you a quick 2-second explainer on why this is true, when you think about a neural network, especially a complicated neural network with many layers and many nodes per layer, there's a lot of weights to train. And when you have, let's say, 1,000,000 weights, but you only have a data set of size 1,000, to put it simply, the model is quite overpowered in this case. There's many configurations of these weights that are going to fit your training and validation data fairly well, but that doesn't necessarily mean that those are the weights that are correct, that are most generalized to the data. To give you a much easier example, let's just say I give you 2 points, and I say, give me a model that is going to fit those 2 points. And if you're using a very simple linear model, there's only one thing I could draw, right? I could draw the line through those 2 points. If you tell me that I'm going to use a higher order polynomial like a quadratic or a cubic, then there's lots of other curves I could draw. For example, with quadratic, I could draw this guy or I could draw this guy, if you see what I mean. So as you have more and more weights in the model, there's many things that work for your training and validation data, but that doesn't necessarily mean that they're going to fit the true trend of the data. Quite simply, there's just not enough data. So the volume required for training is also a very important thing, especially in cases where you don't have a lot of training data to begin with. Interpretability. Very important, very underrated. I've talked about this a lot in previous videos. But put really simply, if 2 models are the same on all metrics, except one is easier to explain and interpret, go with that one. Easiest solution is the better solution. Inference time, as we saw, is very important too, especially in cases where you need the prediction to be served very fast, like a search engine. You can't be taking a minute to make a prediction for a search engine. You need to be doing it in milliseconds. So inference time becomes important there. And finally, storage. We didn't talk about storage either. But some machine learning models take a lot of actual just storage room in the computer or wherever this model is being stored in order to host this model. So I'm looking at k-nearest neighbor for this one. As we said before, k-nearest neighbor is not really a model. It is your training data itself. So if you think about your training data having, dozens of features and millions of rows, you need to just store this thing somewhere, versus a decision tree, again, is just a series of if statements, much more compact. So it doesn't take nearly as much storage to store this guy. And so you might accept a lower accuracy, a lower precision metric on decision tree if it means that your storage is going to go way down. So these are just some of the ones that I've thought of. I'm sure there's others. Again, please put them in the comments below. But the main point of this video is just trying to get across that there is not one way to tell if a model is good. There are many things you need to look at. Some become important, some become not important based on your use case, based on what kind of problem you're trying to solve. So hopefully you enjoyed this video. Please like and subscribe for more like this, and I will see you next time.